Welcome back to the Basics of Biomechanics lecture series. This will be our second set of lectures, and this will be part one. We're going to be talking about kinematics and defining motion. So if we look at the flow chart here, we know that biomechanics is made up of kinesiology, which is functional anatomy, but it's also made up of kinetics and kinematics. And today we're going to be talking about motion and kinematics, because as you know, it's related to motion independent of the forces that cause that motion. And there are two types of motion, linear and angular motion. And within linear and angular motion, we also have position, velocity, and acceleration, which are part of kinematics. So let's take a closer look. Now we know that motion is caused by a force. The only way to get something to move is to apply a force to it. We also have to realize that energy causes a force. Therefore, there's a relationship between energy, force, and motion. Remember, energy is part of exercise physiology, and it's nothing more than the capacity to do work. So if you apply energy to our muscles, it produces forces. These cause the motion on big or small objects. But remember, too, there's also an external, those are the internal forces. There's also external forces, too, which are gravity, currents in water. There could be air resistance, friction, a number of things. So let's start with motion. What is motion? Well, motion is nothing more than the displacement of an object or system from one point to another, or we can say it's a change in position within a frame of reference. We'll talk about that in a minute. Four types of motion: rectilinear, curvilinear, rotary, and general. Remember, when we displace an object from point A to point B, it's a linear displacement, but the path that it takes from point A to point B could be very, very long. So once again, if we look at lifting a weight from the floor to overhead, we would measure from the floor to overhead in a linear fashion in meters. It'd be a straight line, but the path that it takes to get overhead may be completely different. Now, if we look at a system, we talked about this in the last lecture. A system is a body or group of bodies or object to be studied or examined. An example that we gave was the arm. The arm can be an entirely different system to analyze just by itself. But within that particular system, we could have three other subsystems: the upper arm, forearm, or hand. So we know that, there's multiple. If we look at the whole body as a system, look at all the subsystems within the human body, and how do they all move? So this is the foundation of movement analysis, applying the concepts related to motion of a body or its segments and what causes that movement. Our frame of reference here are going to be three dimensions: X, Y, and Z. First X, then Y, then Z. X and Y, if we look here, X is forward and backwards, Y is side to side, and Z is up and down. X and Y, they're perpendicular to ground, and they're parallel to the ground and perpendicular to each other. X runs forward and backwards. Going forward in the X direction is positive. Going backwards in the X direction is negative. For Y, if we move to our left, it's positive. If we move to our right, it's negative. And for Z, it's an up and down or vertical action. If we go up, it's a positive direction. If we go down, it's in a negative direction. Let's look at our examples. A swimmer. The swimmer here, she's moving forward in the X direction. She's trying to stabilize and not go left or right in the Y, and she's certainly not trying to go up and down. Same with the foot. If we look at the foot, it's moving in a sagittal plane going up and down. So it have a y-axis, and when it spins around the axis of rotation of the bike, it's moving in a circular action. So it's going up, it's going forward, it's going down, it's going backwards. So it moves in the Z and it moves in the X, but it stabilizes in the Y. So these are the kind of things you got to look at when looking at any type of movement, especially the human body. So we must identify what environment the system is moving in. Like examples, what's moving, what's not moving, what plane of motion is it working in, and the dimensions, X, Y, or Z. Let's look at the lifter here. As she comes up out of the bottom, once again, she moved that bar from point A to point B overhead. And the path of that bar take did not go straight up, but if you ever look at an Olympic lifter, it'll actually pull in toward the lifter. They scoop and they'll extend their legs and keep the bar close to them in a straight line fashion as possible. That path is going to be slightly out of position from straight up. Now, if you look at the bar, if you look at the planes of motion, it's positioned from left to right, so it's in a frontal plane, but her body is actually moving around a medial lateral axis around the hip, knee, and ankle. Her trunk is going to extend in the sagittal plane. Her hip, knee, and ankle are going to move in the sagittal plane as well. So her trunk is static, but the dynamic action is going to be at the hip, knee, and ankle. She's going straight up, so that means she's going in the Z direction. She's trying to stabilize and not move forward or backwards or side to side in the X and Y. So she's trying to stabilize there and just move in the Z dimension, the vertical. Directions of movement related to the ground or change of body location relative to the ground is our orientation of the body moving in space. And we looked at that orientation of a body described within a spatial frame of reference, or the X, Y, and Z. We looked at motions, linear, curvilinear, and angular. Remember, a lot of times too, angular motion, it's a system attached to an axis of rotation. If you only do a partial rotation there, it's in a curvilinear path. If it does a full rotation, that's a complete circle. So we have to distinguish between those two. If we look at linear translational motion, all parts of an object move the same distance in the same direction at the same time. So if we apply a force to the driver in the car, he moves from one point to another in a straight line. In a curvilinear path, let's look at this. Let's look at the long jumper. He's running straight down the runway. When he hits this board, he'll take off at a certain speed and at a certain angle. And he'll fly through the air, and depending how far he goes will be based on his speed of takeoff and his angle of takeoff. Right there. But he'll travel in a curvilinear path. His body, his legs and his arms will move in a rotational fashion. If you look at the arms, they will spin in 360 degrees rotation, so that's circular action. His legs, each hip, knee, and ankle will also rotate around an axis of rotation, so that's rotational movement as well. But his displacement from point A to point B will be measured in linear units, in other words in meters. The distance traveled is in a curvilinear path or mode of motion, or what we call a trajectory. Now if we look over here, if we're throwing an object, the trajectory of the object that we're throwing will be based on its weight, how much mass it has, how much gravity. The mass is based on its weight is based on its mass times acceleration, the force of gravity pulling down on it. So if you look at throwing a shot put, the trajectory will all be based on its height of release, its speed of release, and its angle of release. So once again, I think we talked about this last time about a short shot putter versus a tall shot putter. A short shot putter will release at a certain height above the ground. Now if he wants to throw as far as the taller thrower, the taller lifter, thrower, will throw at a higher height off the ground, so his angle of release is going to be different. If everything is the same, then if we look at that, the taller lifter will, if everything is the same, the speed of release and the angle of release, just from the height of release, the taller thrower will probably throw farther. So it all depends on those three. Rotary types of motion system is at about a fixed point and moves around this point called the axis of rotation. Joints in the body are considered an axis of rotation. Now, changes in location is called angular displacement. It's going to go in a circle, or it's going to go a curvilinear path that's partial, but it's still considered angular or rotary. And those movement in that angular path is going to be measured in degrees, radians, or revolutions. And in this case, a lot of times in biomechanics, they're measured in radians, and a radian is approximately 57.3 degrees. But for the most part, if we look at qualitative movements that we're going to do qualitative analysis, we're going to go like a bicep curl from the bottom up, and it's usually going to travel depending on the range of motion at that joint and how much mass are on that joint. It's going to go from 0 to approximately 160 degrees range displacement, angular displacement. So once again, it's going to depend, but it's angular motion is measured basically in degrees. So if we look at that angular or rotary movement, all parts of an object move in a circle around a single point or axis of rotation. So if we look at the golfer here, this dotted line is his axis of rotation, and this is considered diagonal movement. The same with the batter here, the baseball player. He will move around this axis of rotation. So we'll apply a force to the object in his hand. The body will rotate in a circular path, as did the golf club as well too. But it all travels around the body. The trunk, which is the system, will travel around that axis of rotation. Same here. If we look at the trunk as the system we're looking at, it'll travel around a axis of rotation. But also too, the arm is considered a system. The legs are considered a system as well too, and they're going to move differently, but everything's based on the trunk action around an axis of rotation. So what's general motion? General motion can be linear in straight line, angular in a circular rotary fashion, or a mix of linear and angular, which we simply call general motion. And in sport and in real life, we have a mix of linear and angular movement, which is most common. That's what we call general motion, or normal human movement. Now, we also have to look at the body's link system. It's a system of movable links or segments, which we call subsystems. Remember, too, if we looked at that, we looked at a whole body system, but we also have different subsystems in there. So let's look at that. We have 11 functional systems or links. The head and cervical vertebra, thorax and thoracic vertebra, the lumbar vertebra, pelvis and sacrum, thigh, leg, foot, shoulder, girdle, arm, forearm, hand. And note, some of these links comprise more than one link, like the vertebral column of the shoulder girdle. But you can see here with the gymnast on the rings doing a handstand, you can see all the different systems that can be identified. So you have to know what those systems are, and also have to identify them when performing a qualitative analysis of any particular movement. Now, the reference also too could be in the different planes of motion. Human movement is referenced from the anatomical position. Convenient but not practical, since most movements are not initiated from this point or from this position. However, we still base all our references of movement from the anatomical position. But it's a very simplistic way to describe and define movements and locate positions of muscles, bones, and various connective tissue. So what is the anatomical reference position? Erect standing position with all the body parts facing forward. This was developed a long time ago. And it's considered the starting point for all body segment movements. Normally, if we look, humans don't really stand this way. They usually stand with their hands at their side and their palms facing inward. So, but for simplistic purposes, we're going to go with the standard anatomical reference position. Now, the cardinal planes of motion. We have the sagittal plane, which cuts the body into equal left and right halves and goes around a medial lateral axis. The sagittal plane is here, and it rotates around a medial lateral axis of rotation. The frontal plane cuts the body into front and back halves, and it rotates around a anterior posterior axis of rotation. Then we have the transverse plane of motion, or what they also call horizontal, because it cuts the body into equal upper and lower parts, and it travels or moves through and around a horizontal or vertical axis of rotation, or longitudinal axis of rotation. So once again, sagittal plane, in which forward and backward movements occur, frontal plane, lateral movements occur, and the transverse plane, in which rotational movements occur. Let's look at that. The medial and the reference axis also be called the medial-lateral axis, also called coronal axis, around which rotations occur in the sagittal plane. We will move, like if we're doing a flexion of our arms upward, we will move through and in parallel with the sagittal plane, the imaginary sagittal plane, but around a medial-lateral axis. If we look at the anterior-posterior axis, it goes, if we're doing raising our arms to the side, we'll move through the frontal plane, but around the anterior-posterior axis, from front to back, through the shoulder joints. Now, if we're turning our bodies, if we're just rotating the trunk, we're moving through the transverse plane, but around a longitudinal axis. And we just went through this, but let's go through it again. Sagittal plane, equal left-right halves, medial-lateral axis. The frontal plane, body, cuts the body equal front and back portions, and associated with anterior-posterior axis of rotation. Transverse plane, also called horizontal, cuts the body to equal top and bottom halves, with associated horizontal axis or vertical axis of rotation running perpendicular or top to bottom through the plane. We also have diagonal planes. So if we look at the high diagonal plane, this could be the baseball player here in a pitcher, upper limbs at the shoulder joint, overhand pitches like a baseball pitch. The mid diagonal, where the trunk is moving, that's like a golf swing. But then we also have low diagonal, the lower limbs at the hip joint. Now, what movements occur in the sagittal plane? If we look at the arms, we have flexion, extension, and hyperextension. We also have, if we look at the foot, we have dorsiflexion and plantar flexion. Once again, let's look at this again. Our knees. If we bend our knees, it decreases that angle at the knee. That is called flexion. If we extend the leg with the knee, with the thigh fixed, and just extend the lower leg, that's called extension. Same with the bicep curl. We flex the arm, that's flexion. We bend it. Then if we extend it, like in a tricep press, that's extension. Same with the trunk. If we bend forward at the hip, that is called trunk flexion. If we move it from the down position to the up position, that is called extension. Movement to the frontal plane, abduction, adduction, raising our arms, lateral flexion, elevation, depression of the shoulder girdle or the shoulder blades, inversion, eversion of the foot, and radial and ulnar deviation. So if you look at our leg, abduction, raise our leg out to the side, pull it in, it's adduction. With our trunk, if we just bend to the left side or the right side, that's called flexion. If we look at our hand, if we move it to one side, ulnar deviation, radial deviation, it's still considered flexion. If you look at the anatomical position, we move our hands out to the side. If our palms are facing forward, move them out. That's ulnar deviation. And then we have radial deviation, inward and outward. But it's still considered movement in the frontal plane around a anterior-posterior axis. If we look at elevation and depression of the shoulder blades, that's in the frontal plane. And the axis of rotation is at the collarbone, that it's attached to the sternoclavicular joint and on the sternum. That's where the axis of rotation is, front to back, anterior, posterior. If we move our foot out to the side and bring it in, that is considered frontal plane movement as well. Now, transverse, left and right rotation, medial lateral rotation, supination, pronation, and horizontal abduction, adduction. If we rotate our leg in and then outward, that's medial and lateral rotation. But it's rotating around a longitudinal axis. Same with pronation, supination, from, once again, reference from the anatomical position. Now, if we abduct our arm and then pull it in toward the midline of the body, that is considered horizontal adduction, but it's still around a longitudinal axis. It's like doing flies, dumbbell flies, or if you look at a bench press, it's still considered a transverse plane movement. Now, once again, let's look at this. What is the movement here? This is what we just talked about. The bench presser. Everything is referenced from the anatomical position, but even if he's laying down, he's still moving the bar in a transverse plane of motion. Now look at that. The bar's going straight up. So if he was standing up and pushing his arms out in front of him, that would be in a transverse plane of motion. It's around a longitudinal axis, which is through his shoulder joint, and pushing the bar away from him. All right, so that's transverse. It's the transverse plane, moving it away from him. What systems are activated? We've got the shoulder girdle. The shoulder girdle is actually considered depressed and retracted. And also, too, the arm is the system here. But he's also got the forearm, the upper arm, and the hand. The hand is fixed. It's stabilized. And the forearm and the upper arm move because there's a shoulder joint there and the elbow joint. And if it's in the transverse plane of action, in the transverse plane, it's going to move around a longitudinal axis at the shoulder joint. So you can see how we're going to look at all these things to identify a system, identify what plane of motion it's in, where's the axis of rotation, and what type of movement it is. Flexion, extension, abduction, adduction, what plane of motion, and the axis of rotation. So this is why you have to know all the systems, all the planes of motion, all the axes of rotation, and also, too, what type of motion it is.